Today I will talk about like a Cohen Jones Segal results, kind of. First, I will give a kind of recap about chain complexes, like in spectra, and maybe frame flow categories. After that, I will talk about the Cohen Jones Segal construction. And after that, I will give a sketch of the proof of the Cohen Jones Segal theorem. Okay, so let's begin with a short recap. So Shauli and Alice told us about like chain complexes, and we saw kind of two definitions. I will give like a third one and kind of shortly compare them to one another. So first, I will introduce the category J. This category will be a topological category. The objects will be like the integers and special object, which we call like maybe infinity or just point. We can think of it maybe just the special point. This will be a pointed category. And the morphism space, like from J between I and J, will be like modeled as R plus, like the non-negative real numbers to the power of I minus J minus 1. And that's pretty it. Like if one of them, like if I or J is the point, then the morphism space will be just a point. And if I equals J, then it will be like kind of the identity and the morphism point, which is the morphism that factor through the point. And did I forget something? And yes, okay. So wait a second. Yes, you can see that. Okay, sorry, I need to compactify this thing. Yes, so you can see, for example, that if I equals J plus 1, then we get R to the, like this thing, compactify. And when I write this little plus, I mean, if the space is compact, then I add a point, like a base point kind of. And if the space is non-compacted, then I compactify it. So for example, this thing is the compactification, like in the sense of one point, which is like S0 as a topological space. And we think, for example, in this case where I equals J plus 1, as like the morphism space have two objects. One of them, one of them is the point object, and one of them is, we think of it as the differential, like this thing will be like the pointed map, which is also always have between any two objects, and di, for example. And we think of this, like this topological space as a topological way to model a higher null homotopies. Yeah, we will see maybe in a second what I mean. Great. So I will maybe put it inside. And I will remind you about the other models for this like chain complexes.
Composition is
Indexing.
embedding of in like the first part of the R.
What?
Composition, how do you define this embedding in the first part of?
Yeah, composition, like you have kind of numbers like x I don't know, maybe to x j, and you have like x j to x k. Maybe here you need to take -1 and here +1, and you embed them like by putting this series of real numbers to xi, xj, 0, xj minus, yeah, maybe +1, j -1, xk. Yes? Yes, and yeah, you do this before the compactification, and you compactify, then you get something. Great. Okay. So you will say something about the like Alice model for how to index chains. So Alice gave us the model of the category with objects are like Z plus maybe the point, yeah, and the more like let's draw the category. The category was like we have I don't know like n -1, n-2, like, and we have like one non-trivial morphism between any like successive objects, and of course we have always the like the point and the map, like the zero morphism. And we like maybe we need to say a few words about how to model infinity categories with topological categories, but you can see that these spaces like these spaces are all contractible. So Alice model and the topological model are equivalent. So maybe up to give a topological model to things, we can say that the pointed functor between this J category to some infinity category C are equivalent to this, I don't know, Z point category, which maybe we can call chains to C. And this is kind of what we call the coherent, maybe coherent chain complexes in C. The third model, which I think Shauli told us about, is by taking like degenerate cubes. Like maybe I will first draw the simple example. We have kind of object A, B, C, and D, and we have like in a category like A, B, C, and they are objects in some infinity category C, and we have like a cube like that. So this thing is a chain complex in the category C. Here we can see more explicitly all the relations between the composition and the null homotopies. For example, in this picture, which is like how we model these coherent chain complexes in, for example, Alice model. We know that this composition is equivalent to the zero map, because like we know that we always have the zero map from A to C, and we have kind of a null homotopy. And here to the left in the Shauli model, we can see kind of explicitly that this back face, like the face with A, B, and C, is the null homotopy, and also the filling of this cube is kind of the higher null homotopy, which you can't, I mean, I can't actually imagine how exactly to model all the higher null homotopies in the kind of Alice model, but in Shauli model, we can see it more explicitly. Like the formal definition was to define the spine in maybe like spine of the natural numbers, which is like a subset. How much time I have? Which is subset of the power set of the natural numbers, which are sets of the form like 1 to n. This is the spine, and this model of chain complexes is like functor from Pn to some category C, such that like f equals like 0, f of set A, f of A equals 0 if A is not in the spine. You want to imagine this kind of cubes that I draw. Okay, these are the three models for coherent chain complexes.
Like, and the third one is like bounded, like a bigger than zero chain,
Yeah,
and
yeah. Thank you.
then you should have like finite subsets of n.
Yes. Yes, I mean, this model like bounded, sorry, bounded chains. Yeah, I mean, I think that I can extend it like to Z instead of N, but I'm not sure if it will be problematic in some ways, and we don't need it, so I will talk only about bounded chains. Okay, on the other end, we talked about like flow categories, which was the categories enriched in topological spaces. And like we have the objects of a category with some function to the integers, like let's denote it by the absolute value, and the home space, like let's C be a, maybe let's call, okay, let M be a flow category. I hope it will be okay. So in the home in M between two objects X and Y are X minus Y manifold is, sorry, is X minus 1 manifold with corners. By that I mean that the dimension of the manifold is X minus 1, Y minus 1, and also the face structure of the manifold is this, again, difference. Okay. Let's, for example, draw a simple example. Like we have 1, 2, 3 objects. And like here, for example, we have like 2 points, and here we have 2 points. And the composition is given by embedding in the boundary. So here I need manifold with boundary where the boundary is like 4 points. So for example, let's take the interval union the interval. And we talked a little bit about how we produce such categories from Morse function on the manifold. And the recipe was that we start with the Morse function on the manifold. Let's call the manifold N, I hope. N to R, and the objects of the flow category will be the critical points of F. The absolute value will be the index, like the index of a critical point X, and the morphism space, which is denoted like that. Sorry. MXY will be the like the unstable manifold of X intersect with the stable of Y modulo the flow action. And we talked a little bit about framing, which is kind of trivialization of the normal bundle of this manifold. Okay. So now we want to talk about like the Cohen Jones Segal construction.
I'm super sorry, Adrie. Could you return back to the slide? And
Yes,
can
of
I
course.
have an obtuse question? You said that this thing that looks like a two simplex, that I should look at it as something two intervals. I didn't really get what you wanted to say. Can you repeat that a bit?
So I claim that this length 2 chain complex is a flow category. The objects, let's write it little bit with details. So I promised you a set of objects. Let's give them names. Let's call them, for example, 2, 1, and 0. Okay? And suggestively, the index of I promised you also an index, which this is the function for to the integers, and the function will be the identity, like suggested by the names. So the index of the point I is just I. Also, I need to provide you these morphism spaces, which are manifolds, maybe with corners. So M2, 1 is the manifold, is the zero-dimensional, zero corners manifold, which is just a manifold, which is 2 points. Also, the manifold M10 is the same. I need to have also a zero-dimensional, zero faces structure. So just a manifold. And the manifold M20 is a one-dimensional, one faces manifold, which is just a manifold with boundary. And the manifold with boundary is given in this case by the union of two intervals. And you can verify that the composition is stand by say that the composition is given by multiplying and embedding in the boundary. So in this case, we indeed have that the 2 points embed in the boundary of the the 4 points embed as the boundary of the two intervals. Okay?
Great, thanks.
Yeah. And as you said, I want to think of this structure as like a chain complex. And you see intuitively that I have this kind of differentials, like the differential from 2 to 1 and the differential from 1 to 0. And also I have a null Bordism between, like I have a cobordism, which is in this specific case, it's null Bordism between the composition, like the d square, which is given by this one-dimensional manifold. And the point, or the intuitive point of the Cohen Jones Segal construction is to give this idea like a formal way, like how to take. So these things from flow, again, maybe frame, we can discuss the G structure later, flow categories to chain complexes in spectra. Maybe I will say that we didn't give the left hand side a structure of infinity category, but the structure of right hand side have infinity category structure. So we do this construction at the level of objects, and we will say a few words about like how to think of extending it to the morphisms on the left hand side, which we call like bimodals. But okay, we will discuss it later. So from now on, we will think about the right hand side modeled by the topologically enriched model. So these things are pointed functor from this indexing category J to spectra. And let's try to write explicitly what it said. So the object of J was like Z and this special point. And so we need to map like, so maybe let's call like F our functor, F like that. So F of I need to be some spectrum. Like let's then, and we need to have maps like Fi wedge Ji J to Fj. And in our special case, the image of this map of realizing a flow category will be such that the
Can you explain what you mean by that? Like Fi is a spectrum, the thing is a space, and you like it's a suspension infinity.
It's, thank you. So it's smashing in with suspension infinity of J.
I'm assuming without the plus because you remember the plus of the point.
And I will write it more explicitly. It's the suspension infinity plus of R. Sorry, the opposite R, never mind. Of R I minus J minus 1. Yes, okay. And yeah, that's right. It compiles, I hope. And let's assume that our Fij's, let's assume that the Fi's are all sphere spectra, which is the unit. So to provide a map, wait a second, maybe write it more suggestively like that. To provide a map like that from this like indexing category to the home of Fi J. In this special case, we get that we need to provide a map from the suspension infinity Jij to the sphere spectrum for each I and each J. Okay. And any questions? Okay. So now let's do it.
I'm super sorry. I am slow with tapping on it on this. How is it clear that the home of from sphere spectrum to sphere spectrum is a sphere spectrum? Is it obvious?
I mean, yes, I'm not sure
Okay.
what is kind of the background that it's clear from, but the sphere is the unit in the category of spectra. That's the point in this case. It's true not just for the sphere, like in general, like home sphere A is A.
It's tensor with the dual of the unit,
Mhm,
which is
okay.
the unit. Right?
Okay. Okay, but you to see that you use some categorical, like you know something about sphere spectrum.
No, it's tensor with the home from something is tensor with the dual, and the dual of the unit is the unit. So
Yeah.
tensoring with the sphere is the sphere. So home from the sphere is the thing.
Yeah. Okay.
Yeah.
Yeah. Okay. 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 Thanks.
Oh, thank you. So let's construct it. Maybe let's put it aside. Will be kind of okay. And we begin with the flow category M. And we give like a kind of this chain complex, which we denote by Fm. We say that Fi is the sum of spheres, where the sum runs over all the objects in M with index equals I. You can kind of index them by sphere X, which indexing the object. And now, okay. We need to say a few words about framing. So I will try to say exactly what I'm using.
Sorry,
By the way,
I'm confused now. What is F now? Like F earlier was the sphere, and now it's a samosphere. It's not the same F probably, but I'm kind
yeah. I mean, you're right. I now using the fact that I can say the same thing. Like if the Fi's are sum of spheres, then I need to provide you a map like that for any X, Y, for any I and J. Sorry.
like you give me a matrix now.
Yes, exactly.
Okay, good.
So for any, so here in this notation, I need to provide you like a bunch of maps, suspension, infinity, J, ij to sphere for any X and Y, where the index of X is I, and the index of Y is J, right? Yes. Okay, and the maps are coming, they have kind of two steps. So first I'm taking my MXY and embed it in this R I minus J minus 1. Maybe I need to add some copies. This embedding exists because kind of like similar to the Whitney embedding argument, like every I don't know, like K corners manifold embeds in this RK plus RK blah, blah, times maybe some R to the N. So we embed our morphism manifolds like that. And now we're doing the Tom collapse map, which is
Quick question. Again, is it important here that you embed it in a way where the strata kind of line up?
yes. I mean, I need to take the like the K L maybe, I don't know, like the L face of MXY to the L face of R ij minus 1 times R. Yes. I mean, the point is that I can do all these things, and after that, I need to convince you that all these constructions are compatible in the sense that they provide me all this, they provide me a functor and not just a bunch of things. So the functoriality will came from the fact that we are doing all these embeddings in a proper way. Yes, thank you. And by collapsing, and by that I mean we can take kind of the normal bundle of MXY in this embedding. You can look at it here. Also, I don't think we discuss about it, but we have kind of the theory of stratified vector bundles, which is kind of the if manifolds have bundles and manifold with corners have kind of this I don't know, let's call them maybe stratified vector bundles, which is kind of cubical diagrams in the of vector bundles. Maybe if I will have enough time, I can say a few words about it. And by taking this embedding, again, kind of level-wise, like for each strata, and by collapsing the things which are outside the normal bundle, we get a map in the inverse direction, which is map like that, or I minus j minus 1. Thank you. Times r to the n compactified to the compactification mxy, which also called the Thom space of mxy. This thing, like kind of the like there is a connection between the Cartesian product and the compactification, which make this thing to be the smash between them. So we get like a sphere n smashed with this kind of what we call j I j. So we got a map like that. This will be the will be half of the map that I promised you, like this family of maps. Okay. Now to get the other half, you need to provide your map from the Thom to the sphere. And now we need to use the framing. So basically a framing is a trivialization of this normal bundle. So if you provide me a framing, which is a isomorphism x and y times. Now I need to calculate the codimension properly. The codimension is just n. Yes. And the this comes from the fact that the dimension of mxy is like, again, this number, the I minus j minus 1, not just the face structure, but also the dimension. So given a framing like that, maybe denote the framing phi xy. Sorry, we can project to the right coordinate. And compactified. So we get kind of, let's call it, I don't know, phi xy prime is a map from nu mxy plus to the compactification of the n-dimensional Euclidean space, which is the sphere n. So all in all, we got a map like that, and we compose this map together with this map to get a map from sphere n j I j to sphere n, and by taking kind of suspension infinity and suspending minus n times, we get a map from suspension infinity j I j to the sphere. And maybe I will say that the first map, the first half of this map, like the first composition, like this one, is not depend on the embedding. I mean, I kind of choose an embedding, but if we take a big N, like the thing we embed in, to be like large enough, we get that the space of embeddings is contractible, so it don't depend on the specific embedding. But the second half of the composition, like the map phi xy prime, is depend on the framing. So different framings give you different compositions like that, and at the end, they will give you different chain complexes. Questions about this procedure?
Can you do it without topological the model? Like, is it something like the Baker-Gottlieb transfer of MXY of the point? Like, you have the map from the point to the manifold, and it's dualizable, so you take the dual. Is it the Baker-Gottlieb transfer of this map or something like that?
Yeah, I think so. I mean, I think that the first half is kind of just by taking duals. Like you dualize you take the dual of MXY and you embed it. I mean, I think that is yes, but I'm not sure what are the exact details, if it's the same or not, but I think so. I mean, I must admit that I don't know how to construct this kind of a functor between flow categories to chain complexes, where it was like this one. I'm not sure how to construct it like without the topological model. Okay. Yeah, so maybe let's try to do for example. So let's take, okay, so maybe let's do it maybe the very intuitive example. So let's take RP2 and I will begin with a Morse function. I will create a flow category and then I will realize this flow category to a chain complex. And
So we are not explaining why compositions go to compositions?
I mean, wait a second.
It might be clear and I just don't see it.
No, I mean, it's just the kind of the following commutative diagram. Okay, so you side, we know that M, X, Y, M, Y, Z, like embeds nicely in M, X, Z. So now you take, nu of all this stuff and nu of all this stuff and embed that in J, like IJ and J, JK, and here you goes to J, IK, and this is the composition in the top of J category. So this kind of the reason which this thing is a functor. I mean, I totally didn't give you all the details, but it's kind of coming from the fact that you can kind of do this and all this thing, and kind of the functoriality of the collapsing. Like maybe I want to say a few more things. So like you have, let's do it. You get kind of a map. Yeah, you get the map J, I, J to nu MXY to the sphere and J, JK and nu MYZ to the sphere. And now you can, like smash them together and you get like this thing. But on the other end, this thing, this diagram on the left is commute. And I mean, okay, maybe if I will have like time at the end of the talk, I will say a few words, but basically it's the fact that you can, like this diagram is commute. Okay, so let's go back to this toy model. So we begin with this Morse function. Maybe I will draw the intuition. So we have this thing. We take the Morse function, which give us kind of a, okay, let's write it. It's x squared plus 2, sorry, y squared plus 3z squared, which is kind of, it's a function R3, but you can see that it define a map on the projective space. Yeah, I don't think I have time to go to all the details, but we have like 3 critical points. This, for example, it's, yeah, this thing have index 2, this thing have index 1, and this point have index 0. And so we get flow category M, which is given by kind of 3 objects as I draw them exactly. And the flow lines between the point of the critical point of index 2 to point of index 1 is this flow line, and the one that goes like on the other side of the hemisphere. So these are 2 points. I don't do all the framing thing, but you can, I mean, you may believe me that the framing on these 2 points, like the one which represent the nearest flow and the one which represent the back flow, have the different framing. Like one of them is kind of a plus and one is minus. And on the other end, there are 2 like ways to flow from 1 to 0. We will denote them maybe by this point and this point. This is the representative of these 2 flows. So again, we have like 2 points. They have the same framing, and there are okay, and the moduli space of flowing from 2 to 0 is kind of represented by this thing, this thing. And indeed, as I just gave an example, the moduli space between like the point index 1 to the point with index 0 are 2 intervals with the kind of trivial framing. I mean, these, okay, I mean, we don't need even to discuss about framing in this scenario. So yeah, we have kind of 2 intervals with, I don't know, you can choose whatever orientation on the intervals that you want, and you get that the boundary of them is exactly like that. Okay, now we want to realize it to a chain complex, and we get a chain complex with 3 spheres. Sorry, I just made a mistake. This is the right framing. Oops. Okay, so to get the map between the first sphere and the second sphere, sorry, between the second sphere and the between like the one connected to the critical point of index 2 to the one with index 1, you need to kind of take, for example, copy of S1 and copy of S1 and take 2 points and, sorry, and take 2 points and take a normal neighborhood, like a tubular neighborhood, like that, and like that, and frame them according to the framing. So we choose a basis to the right and again another basis to the right, and by collapsing all the area which outside the normal bundle, like by collapsing all this and this stuff, we get the map that goes this direction, and then wait a second, yeah, and like I don't know, the map that goes like that, and then like goes backward like that. Yeah, this and on the other end, if we take the other framing, which have like we choose like this one as a basis, but on the other end, this one as a basis, we get the map that goes around S1 twice. This again, this is the collapse map. In the case of S1, we say we don't mind which dimension we embed our manifolds, so we get the answer. So we get like this thing is null homotopic. This is the thing that goes back and forth, and this thing is the thing that goes twice. So this map is the multiplication by 2. And okay, it's maybe less intuitive, but the null homotopy, this one, from like the first sphere to the last sphere, is the trivial null homotopy. And if you want to understand, like in terms of filtered spectra, what the result, you need to take iterated cofibers or things like that. So, I mean, okay, I think we have enough time for that, but let's try to get enough intuition. We have like a sphere go to sphere by multiplication by 2, and here we have like 0, and we have a square like that, where the filling is the trivial one. And to take iterated cofibers, we need to take like cofibers to the right, and we get kind of the suspension of RP2 goes to S0, and by taking cofiber, we get the suspension infinity plus, sorry, this is suspension infinity plus maybe -2 or something of RP2. Okay, sorry about like the lack of details, but the point that I want to say that this is always the scenario. So let's write it more carefully. If we start with the Morse function on a manifold, we can get, as we saw in the last talk and also in this one, a framed flow category. And as I tried to tell you today, we can get a coherent chain complex in spectra by this kind of collapsing. And at last, we can take this chain complex and take the associated filtered object by taking like total cofibers. So we get object like filtered in spectra, and by taking colimit, we land again in spectra. So
Just
on the other hand,
to make
yes,
sure, if I take the chain complex over spectra and I push it to Z, do I get the regular the Morse complex, right?
yes. Yeah, I mean, exactly. You forget all the higher coherences and you just get, I mean,
So and the complex will always be probably like sum of spheres, and like the maps will be just like the
yeah.
matrices of like the corresponding chain complexes, and then the extra data is the more homotopies, right?
Yeah, exactly. Maybe I will
Cool.
write what you said. So on the one hand, we can just take here suspension infinity plus, and the Cohen Jones Segal theorem say that indeed this diagram commutes. I mean, I can do all this tedious construction to get a flow category and a chain and filtered object and spectrum, and you get that this is the suspension infinity plus of the manifold itself. And
what do you
as
mean by
mentioned,
this
Shaoli,
diagram compute? Like the source is not a target, this is not a category. Is it like a category of is it a
yes,
categorical statement or is it like per object statement?
no, it's an object-wide statement. Yes. And as you mentioned, Shaoli, you can like do this thing and you get the Morse homology, of course, like the Morse complex. Yes. Indeed. So, I mean, I'm not sure what is the, okay, we can try to guess what is the categorical statement if there is a categorical statement. I don't think that I'm sure. I mean, for example, at the end, if you choose like different Morse functions, you get like the same homotopy type, but you get maybe different, I mean, of course, you get a different chain complex and flow category and the filtration. Yes, yes. But this is, I mean, it's a good question. Can we put some categorical structure on the category of manifolds with Morse functions? I'm not sure. Yeah, and well,
I'm sorry. I'm
yes,
super sorry to this like open question. Like, if I know what a flow bimodule is and what like Bordisms of flow categories are, isn't that the categorical structure you're looking for?
The problem is that it's not clear what is the category of manifold plus Mars function, but this is a functor form, not the flow category one. Just to
like
correct me.
I agree that we talked about the connection between bimodules and like different Morse functions, but I'm not sure like what is the structure to make this diagram commutes. Like maybe I will say something else, which connecting to this story, something which is kind of more clear and formal that we can do, which is kind of the Abu Zaid Bloomberg result, and we will talk about it later, is to talk about the connection between chain in spectra, maybe such that Fi's are sum of spheres. This is like subcategory of chains, and we can talk about frame flow categories as an infinity category, like the category that we talked like last week was the homotopy category of this thing. Like indeed the object are flow categories and the morphisms are bimodules up to cobordism, and the Cohen Jones Segal construction that we just described give you functor for this direction, and indeed all the discussion about the conjectures of this being the same as that is kind of like we can localize kind of and get the category of spectra, and there is a result that after kind of localizing some data in the frame flow category, we get that this thing is a model for spectra. And if we don't localize, like we don't throw some, like identify some relations, I don't think it's written, but it's like, it needs to be that these two categories are equivalent. Like frame flow categories with bimodules and all the higher structure are chain complexes in spectra. So this don't give an answer to the structure on the category of F and M's, but it give answer to the second part of the I don't know, like this part of the diagram.
But I guess to get the equivalence to chain complexes, you have to localize up to like quasi isomorphism, right? You can have morphisms of frame flow categories that don't give you like level-wise equivalences.
Wait, say it again.
You can take two different cell structure on the same spectrum that will give you different
Yes.
chain complex.
Exactly.
Yes, I agree.
So you need to localize by this kind of relations, which is what tricky. So
So yeah, I think that time is over.
Yeah.
I
Thank
mean,
you.
yeah. The goal was to describe like a very rough sketch of the proof of the this claim about the commutativity object-wise. But yes, I mean, I'm not sure even if the literature have a good proof, so never mind. Okay, let's stop the recording, and you can